Let's look at 47. And here's limit as x approaches infinity from x to the third times e to negative x squared. Normally, the product of 0 times infinity really requires a simple, maybe I shouldn't call it simple, algebraic manipulation. Not changing the function, but changing its presentation. Normally, that's what we are looking for. So first of all, let's see what this is all about. So when x approaches infinity, where is this going?
Infinity.
Thank you very much. When x approaches infinity, this piece is going where?
Negative infinity.
Very good, awesome. And now I'm asking about this piece. E to negative infinity, where is that going?
Infinity.
E,
Negative.
careful, careful. If the power is negative, it doesn't mean that the answer is negative. Be careful, please. So this is 1 over e to infinity. We wrote this many times, so please try to understand this. This is very important. Where is this going then?
0.
Excellent. Voila. So the case is 0 times infinity. So we are going to try to work on this function and present it differently. So let's see, is there another way of presenting that function? Anyone has an idea here? Is another way, not changing the function, but presenting it differently. So it's the same function, but I used an algebraic manipulation. Any suggestions?
Could you maybe x third over 1 over e to the negative x squared?
Absolutely, absolutely. Very good, awesome. Now again, where is this going?
Infinity.
Good. Where is this going?
Zero. Infinity.
Right, because it's e to infinity. Do you like this? Of course. This was just really nothing. It was very easy to change this product into this, which we love, or maybe just like. So, not n, x, approaches infinity. So now we differentiate the top. What do we get?
X squared.
Excellent. We differentiate the denominator. All conditions are fulfilled. It's a limit, it's infinity over infinity, both functions are differentiable, and it's a ratio. We're differentiating this.
E to the x squared
Excellent.
times 2x.
Awesome. Brilliant. Very good. I get rid of a 1x. So then I continue. Let me write it one more time. So this is x approaches infinity. The top is 3x, and the denominator is 2e to x squared. 3 over 2, they're both factors. They can go in the front if that's what you want. But don't forget that they are there. Where is the numerator going?
Infinity.
Very good. Where is the denominator going?
infinity.
Very good, awesome. So L'Hopital's rule again, 3/2, limit, as x approaches infinity, the top you'll say 1, I'm sure, and then e of x squared times 2x. Good. And now, where is this going?
Infinity.
Very good. What is the answer? 3/2, 1, infinity.
Zero.
Very good. Which means y equals 0 is a horizontal asymptote for this function at infinity. Because this is not a pure rational function, we cannot conclude anything else. And I have students who say, really, didn't you know that 0 times something is 0? No. No. Do not assume. You cannot assume that 0 times infinity will always give us 0. So don't even try. It's an indeterminate case. No one can come up with the answer before we analyze step by step. So bottom line, 0/0, infinity over infinity, L'Hopital's rule, 0 times infinity, normally a very simple algebraic manipulation, changing the function into infinity over infinity or 0/0, so we can apply L'Hopital's rule. So now let's look at any questions on this. Anyone? Any questions? Okay, so now let's continue with those products. I meant powers, of course. I didn't mean product. There's only one product. So let's look at powers. Okay, here is one. So limit as x approaches 0 from the right of x raised to the square root of x. Let me refresh your memory. The three powers are 1 to infinity, 0 to infinity, and infinity to 0. All indeterminate cases we cannot conclude. 1 to infinity is not 1, 0 to infinity is not 0, and infinity to 0 is not 1. Do not assume anything. No assumptions here. Okay, good. So where is this going?
One to infinity.
So when x approaches 0, x approaches 0. When x approaches 0 from the right, where is this going?
Zero.
Good. Okay, how much is 0 raised to 0?
I'm probably stupid, but 1?
Well,
Isn't anything raised to 0 1?
a raised to 0 is 1. A raised to 0 is 1 as long as a is not 0. So any number raised to 0 is 1 as long as the base is not 0.
0 then.
So we have to analyze this step by step and see what we come up with. So did I lose anyone? So it's a very good point you're making, but 0 raised to 0 is 1 as long as the base is not 0. Okay? So I would write 1 in this particular case, but what I would highly recommend is go through the steps. So let's go through the steps before we decide anything. So let me refresh your memory on something very important. Whenever we have a function raised to another function, I'll come back to that. So when we have a function raised to another function, how do we find the derivative of something like this?
We subtract 1 from the exponent.
Careful. So this is a function and this is a function.
Power rule.
Careful.
Chain rule.
Careful.
Logarithmic differentiation.
Thank you very much. So this is 0 raised to 0, sorry. I was just thinking about that. So indeed, apply log. Of course, natural log. Good. So now we're interested in finding a limit from a function raised to another function g. So this is a function raised to a function. When we want to find the derivative, we have to apply log. We name this y and we apply log to both sides, as we did before. But now what about the limit? So whenever we encounter something like this, the derivative requires log. Now we encounter this, it's the same thing. Must apply natural log. So every time we have a function raised to a function, we have to, and we are asked to find the derivative, we apply log. A function raised to a function, we're asked to find the limit, we have to apply log. Same thing. Okay, so I don't want to write anything yet because 0 raised to 0 is an indeterminate case. Okay, so we name the function. So there are many steps here, and we will choose more examples than one. So there are many steps, so please bear with me. So y is this function. In step number 2, as we discussed, we always apply natural log. We have no differentiation rule, and even the limit requires natural log. So I apply natural log to both sides. Natural log y equals the square root of x times natural log x. There is no discussion about the derivative now. We are interested in something else. We're interested in the limit. Okay. So now in step 3, I apply limit to both sides. So then limit of natural log y when x approaches 0 from the right-hand side equals the limit as x approaches 0 from the right-hand side from the square root of x times natural log x. You can say, wait a minute, what are you doing? You're not asked to find the limit of the log. You're not asked to find the limit of the log of that expression. Bear with me, we're going to get back to it. Good. In step 3, we have to continue, and we will analyze what this is. So this, I know you're going to say approaches 0. And does anyone remember when x approaches 0 from the right, where does the natural log go? Remember the graph and tell me where it's going.
Infinity.
Negative infinity.
Negative infinity, yes. So the graph is this. Please remember the graph of natural log x. As x approaches 0 from the right, the function values approach negative infinity.
Which one was the one that is basically that, but it comes from the top and goes to the right?
You mean like
Was
this?
that 1 over x?
You mean like this?
Sort of. But it's
So-
in the top right domain and the bottom left one. Is that 1 over x?
Oh, yeah. 1 over x is this.
Okay.
Natural log is this. If the base is a number less than 1, then it will look like this. But the base is greater than 1, strictly greater than 1, so it's an increasing function. But if the base would be less than 1, log base 1/2, then it will look like this. Good. So it doesn't matter if it's infinity or negative infinity. That's not important. Okay, so it's still the same thing. It's the product. Okay, so what do we do with the product? A simple algebraic manipulation. Do not touch natural log. If you bring natural log to the denominator, they will be very difficult to differentiate. So don't ever move natural log. Natural log has positive power, so it will stay at the numerator, in the numerator, and I will change this and put it in the denominator. So this is power x to 1/2. But if I put x to negative 1/2 in the denominator, I get the square root of x. It's the same thing. So a quantity with a negative exponent in the denominator, it goes to the numerator with a positive exponent. If the numerator has a negative exponent, then it goes to the denominator with a positive exponent. And now at this point, I have this 1 over, so it's, if this was 0, this will be infinity, because this is 1 over. So this piece is 1 over the square root of x. If this approaches 0 from the right, this will approach infinity. So now finally, I'm in this situation, so I can differentiate. So I have limit as x approaches 0 from the right. The top is 1 over x, and the denominator is ugly, but it's not going to be a problem. In a moment, you'll see. So x to negative 3/2. We continue. So we have limit as x approaches 0 from the right. This is in the denominator, so I'll flip it. It's negative 2. This goes now to the numerator, and this goes to the denominator because it's 1 over x. So I have x to 3/2 over x. So x to 3/2 over x. So this would be x to 1/2, limit as x approaches 0 from the right, negative 2, the square root of x, and this is indeed 0. In step 4, so let's summarize for a moment before we continue. We took the function, we applied natural log to both sides. Then in this equation, if you want, we applied that limit to both sides as x approaches 0 as we were given. So limit of this equals the limit of the square root of x times the square root of x, natural log x. This was the product. Don't touch natural log, leave it alone at the top. But change this into x to negative 1/2. It's the same thing. Now differentiate the top because they are infinity over infinity. So differentiate the top, 1 over x. Differentiate the denominator. This has power negative, so it goes to the top. And this is the denominator of the fraction. So then when I copy the base and subtract 3/2 minus 1, I have 1/2, so this is the square root of x. Negative 2, the square root of x as x approaches 0 from the right is 0. At this point, I copy the beginning limit as x approaches 0 from the right of natural log y, and I write 0. I copy the beginning and I copy the end. At this point, I'm going to use a theorem that we used in differentiation rules, in limit laws, and I mentioned that I was going to use it later. It's called the swapping of operators. A long time ago, we discussed this. Let me give an example before I do whatever I need to do here. We looked at the limit of f of x raised to power n as x approaches a. This is an operator that is the outer operator, out. This is the operator that is in. It's the one that touches the function first. But I can swap them. I can put this as the second operator, and I can put this as the first operator under continuity. So I can say limit of f of x as x approaches a, everything raised to power n. So I swapped the operators. I put the limit next to the function, and I put n outside.